Today's lesson will discuss the heat in changes of state. The tools that we need out today, we'll need our note pack opened to page 7. We will need our calculator and something to write with. When you have that ready, please begin the video lesson. We look at today something called a phase diagram, and when we think about the energy changes of state, what they're referring to is the phases of matter are in 3 different states. They're solids, liquids, and gases. And exchanging between those phases of matter either releases or absorbs energy. The heat, measured in joules or in kilojoules, will be found by discussing those phase changes in this lesson. And we begin by looking at something called a phase diagram. You see one now right there on page 7. We notice that phase diagrams display the state of a substance at various pressures and temperatures and the places where equilibria exist between the phases. The phase diagram allows us to see what temperature and pressure the solid, the liquid, and the gaseous form exist in terms of temperatures and pressures. Notice the arrangement of the molecules to the far left in the solid phase, very tightly packed, very organized. To the right side you see the liquid phase, a little more spread apart, the freedom to flow past each other. And in the gaseous phase, there is no organization. Notice the kinetic molecular theory would say they are moving quite rapidly in chaotic motion. There are line segments on this graph we need to become familiar with, and the vocabulary as well as phases change from one form to another. We're just going to label each one of these lines and discuss the terms one at a time. So on the x-axis, you notice we have temperature. On the y-axis, we have pressure. As the pressure and temperature increase, moving up the y-axis and over towards the right on the x-axis, you can see the phase changing from solid to liquid to gas. One of the interesting lines that we'll look at first is line segment AB. Line segment AB begins, of course, at point A, labeled the triple point. And point B up high is called the critical point. This represents the equilibrium that lies between the liquid form of matter and the gaseous form of matter. We label this line the liquid-vapor interphase. Point A we called the triple point. Notice that all 3 states of matter exist at one particular point of pressure and temperature. The triple point would have solid, liquid, and gaseous phase of matter all in equilibrium. At any particular point along the AB line, we would simply distinguish them as the interface between the gas and the liquid phase. Up high, that point B was called the critical point. If we raise the pressure so high, or the temperature so high, we can no longer distinguish between the liquid and the gaseous phase. The critical point ends the line segment A to B. At some point, liquid and gas turn into plasma. They are indistinguishable forms of that matter. Each point along this line segment AB, is known as the boiling point of that substance at that particular pressure. For instance, we've always said that water boils at 100 degrees Celsius, but truth be known, that's pressure dependent. When we say 100 degrees Celsius, we're assuming standard pressure of 1 atmosphere, standing right at sea level, not high on a mountain where the air is thin so pressure's lower, or way down deep in a valley where air is a little bit thicker so it's a heavier pressure. Water would actually boil higher down in a valley and lower than 100 up high on a mountain. Anywhere along that line segment AB would be called its boiling point. Another interesting line is line AD. We're going to label this the liquid and solid interface. Line segment AD separates the solid and the liquid phase. The melting point is found at any particular pressure along this line. The melting point When solids turn to liquids is known as melting, or when liquids go back to solids, we call that freezing. We can see that exchange in the line segment AD. So melting points are found any point along line segment AD. Below point A, the substance cannot exist in the liquid state. Notice the liquid form of matter no longer exists at very low temperatures and very low pressure. We create an equilibrium between the solid phase and the gaseous phase. When a solid turns directly to a gas, that's called sublimation. And if a gas goes directly to a solid, that's called deposition. Dry ice is a great example of a substance that will sublime at ordinary room temperature and room pressure. A block of dry ice is solid carbon dioxide. The solid immediately turns to the gaseous form at room temperature and pressure. So the sublimation point is the equilibrium between the solid and the gas. Very few substances sublime directly at room temperature and pressure. Flip your page in your notepad and you will see this particular graph with me. I place this in here just to remind us of some vocabulary we need to remember or to familiarize ourselves with. Notice at the very bottom, the lowest state of energy is the solid phase. On the y-axis, the energy of the system is increasing. In other words, I have to input energy to head up from solid to liquid to gas. Input of energy into the system we well know as endothermic process. Looking down from gas to liquid to solid, these represented by green arrows, the words condensation, freezing, and deposition, they are lowering the energy of the system. Therefore, we know that to be exothermic. Melting, vaporization, and sublimation are endothermic processes. Perhaps you should make a note of that in your notepad. Heading up, endothermic. Heading down, exothermic. So the process of changing phase will either release or absorb energy, and we'll be asked to calculate based on the amount of sample how much energy is either being absorbed if we change phase from solid to liquid or liquid to gas, or how much energy is being released if we head down on this graph. A gas that condenses to a liquid or a liquid that freezes into a solid can all be calculated. This is a diagram that allows us to review the vocabulary words associated with phase changes, and it does a nice job reminding us of the endothermic process heading up and the exothermic process, the green arrows heading down. We'll need to keep track of those in terms of a negative or a positive sign when we calculate delta H, the heat. The energy associated with states of change. This is a diagram also on your notepad, although I believe these fill in the blanks are above this graph on our page. Here they're down. I typed mine below the graph, just a little different place than what you're seeing on your page. We need to define the heat of fusion. That is given a symbol delta H FUS, the enthalpy change associated with changing phase from a solid to a liquid. A solid to a liquid is known as the heat of fusion. Now in this particular slide, they're showing us some examples of heats of fusion, and they're colored in purple, pink, whatever that might be. They're the bottom part. Butane, 5 kilojoules per mole. Diethyl ether listed as 7. Water is 6, and mercury much higher, 23. Water will be one that we end up memorizing because we use it so often. 6.01 will be the number we plug in. Now what that means, it will take 6 kilojoules of heat energy per 1 mole, which is 18 grams, per 1 mole of solid ice to simply melt. Inputting energy into the system to change a solid into the liquid, requiring energy, 6.01 kJs per mole. The next number we will use so often you'll end up memorizing is called the heat of vaporization. Notice that they give us several different values, again, for butane, 24, diethyl ether, 29, water, 41, and mercury, much larger, 58. The heat of vaporization. How much energy do I need to put into a system to cause a liquid to turn to a gas, to vaporize? That symbol is delta H of vaporization, the change in enthalpy associated with a liquid to gas phase change. Notice, and the bar graph does a nice job showing this as well, it takes an extraordinary larger amount of energy to cause a liquid to go to a gas than a solid to turn to a liquid. Heats of vaporization are always much larger than the heat of fusion. To turn a liquid to a gas requires more energy than a solid to simply melt. These values we need to memorize, work toward memorization, work to kind of remember where to look them up at least. For water, the universal solvent we will use very often in the chemistry lab, we need to remember the heat of fusion. On our bar graph a moment ago it's listed as 6, but when we actually calculate the number we will use, 6.01 kilojoules for every 1 mole of water. The heat of fusion of water, 6.01 kJs per mole. The heat of vaporization, or enthalpy of vaporization, for water is 40.7 kJs per mole. 6.01 kilojoules are needed to cause solid ice to melt to liquid water. For liquid water to vaporize into steam, 40.7 kJs for every 1 mole. The term sublimation is when a solid directly goes to a gas bypassing the liquid phase, and you can simply find that by adding the heat of fusion to the heat of vaporization, which would give us approximately 47 kJs per mole. The sum of the delta H of fusion and delta H of vaporization. These values are now going to be used as we start looking at temperature graphs and heat added. We're going to be asked to take a look at, one line at a time, how much energy is being input into this system, and very importantly, the sum of all of the energy going on from point A to point F. Pause with me here and just really study this graph. This graph shows temperature on the y-axis starting very cold, -25, and warming all the way to 125 degrees Celsius. Notice at line segment AB, from point A to point B, we're below 0. Water is in the solid form we commonly call ice below 0 degrees. So any energy that we're adding to the system from point A to point B, all of that heat energy is being used to simply warm the ice from point A to point B. Whenever we see a slope on the line, such as AB, or line segment CD, or line segment EF, those 3 line segments represent changing temperatures. All of the heat is being used to change the temperature, to warm up that form of matter. Those are MC delta T equations. I'll repeat that, very important. When we see a slope of the line, such as line segment AB, or line segment CD, or line segment EF, notice there's a slope. We have a change in temperature occurring at those 3 areas of the graph. To calculate heat, Q equal MC delta T, a familiar equation. But notice where the line is flat. Line segment BC, that's a phase change. Notice how it's labeled. Ice and liquid water it's just melting, a phase change from ice to liquid water. At point B, it's all solid ice, but by point C, it's now converted all into liquid water. There is no temperature change during a phase change. All of the heat energy is being used to melt the ice, to overcome those intermolecular attractions from solid into a liquid form. We know that value, we just wrote it down, 6.01 kJs per mole. We defined that as the heat of fusion for water. Line segment BC represents delta H of fusion. Look higher, line segment DE. Notice it's flat. No temperature change associated with that phase change. All of the heat energy being put into the system is being used to change the liquid form of water into the gaseous form of water called steam, overcoming the intermolecular attractions of the liquid molecules, separating them into a gaseous form. We know this value for line segment DE. We just defined that as the change in enthalpy, delta H, of vaporization. We wrote that value down, 40.7 kilojoules for every 1 mole of water. We have a total of 1, 2, 3, 4, 5 line segments. Line segment AB, warming up ice. Line segment BC, melting. Line segment CD, warming up water. Line segment DE, turning water into steam. And line segment EF, warming up steam to an even hotter temperature from 100 to 125. This graph, in all of its line segments, can be used to calculate the total heat being entered into the system. Notice this positive slope. It's showing us an endothermic process. We're inputting heat. Heat is getting added to the system, endothermic. So the heat added to the system at the melting and boiling points goes into pulling the molecules farther and farther apart. That's what a phase change does, breaks apart intermolecular attractions. The temperature of the substance does not rise during the phase change. The phase change have flat slopes, no delta T. To calculate the total energy being applied to this system, we simply solve for each line segment and then sum the energies to find the total. We'll go to work doing that very thing. This is where our calculator comes out. This very graph represents sample problem number 1 on our notepad page number 9. Let me read that sample problem for us. Follow along. We're being asked to calculate the enthalpy change, that's delta H, how much heat is being entered into the system. Calculate the enthalpy change upon converting 1 mole of ice at negative 25 degrees Celsius. Notice that was the starting point on our graph. Point A is at negative 25. We're going to go all the way up to create steam at 125 degrees Celsius, and we're under a constant pressure of 1 atmosphere. Now, all the way from negative 25 to positive 125, the initial temperature negative is point A. The final temperature, notice up at point F, is 125 degrees. But friends, there are 2 other very important temperatures that we're expected to know between negative 25 and positive 125. Those are the temperatures at which we have phase changes occurring for water. We know water freezes or melts at 0 degrees Celsius. That's a point we need to plot as well. And we know we'll have a phase change again at 100 degrees Celsius. So when we're going all the way from negative 25 to positive 125, we have to plot that graph and actually figure out how many different line segments we need to solve for. We've already counted for this. There'll be a total of 5. Other constants that we'll need to know in order to calculate. We're given specific heats of ice, water, and steam in the following order. Now, specific heat is the C when we MC delta T. Ice has its own unique constant, 2.09 joules per gram Kelvin, or joules per gram Celsius, either way. Liquid water, we're working to memorize 4.18 or 4.184 if we include that third decimal, joule per gram Kelvin. And 1.84 joule per gram Kelvin is the specific heat constant for steam. We don't have to memorize all three of those values. They're typically provided in the story problem. The other constants we've just written today for the first time. The heat of fusion, given to us is 6.01 kJs per mole, and the heat of vaporization for water, 40.67 kJs per mole. Those values are just there, so they're handy as we go through and begin solving each line segment one at a time. Let's begin, and I gave you plenty of room to write down in the bottom of page 9. We're going to be working a total of 5 problems. The next series of consecutive slides is going to show one problem at a time. So let's begin taking a look at line segment AB. Remember where we are, from negative 25, warming it up to 0. When we MC delta T, because we have a slope of the line, we know it's a Q equal MC delta T problem. I'm emphasizing when I say M, it does not stand for moles. MC delta T is mass in grams. This problem, if you reread, said we're converting 1 mole of ice. But when I MC delta T, I need to have that converted into a gram. It's just an old mole map conversion heading from the scale into the mole. We need to have grams of water when we MC delta T. We can see that 1 mole of water times its molar mass of 18 grams per mole easily converts. 1 mole is the same as saying 18 grams. 1 mole of water would weigh 18 grams. That's the M I place into the MC delta T. So my M, we're going to place in 18. The specific heat of solid ice was given to us in that first bullet as 2.09 joules per gram Kelvin. And how much did that temperature warm from negative 25 to 0? Notice the change from line segment A, B. Negative 25 to 0 is a change of 25 degrees Celsius. Now you hit that with me on your calculator. You hit 18 times 2.09 times 25 degrees. Your screen should read, as mine does, 940.5, and that stands for joules of heat. We've had to input 940.5 joules of heat to move from point A to point B on our graph. Line segment 1, an MC delta T problem. But now I notice we've got AB solved for. We take a look at line segment B to C. The next in the series of 5 problems is a phase change. The very definition of the phase change from solid to liquid is called the heat of fusion. This is the constant 6.01 kJs per mole. What's nice, line segment BC, if I solve for 1 mole, is going to equal that very value. That was convenient in this problem. We were given 1 mole of ice. 1 mole times 6.01 kJs over 1 mole cancels the mole, and we've simply converted to kJs of heat. So line segment BC, as you write this portion of the problem down, you will need to write exactly as I have on the screen. BC equals 1 mole, and that represents 1 mole of ice, times 6.01 kJs set over 1 mole. That will equal 6.01 kJs of heat, an endothermic value. Heat being added is a positive value. So we've traveled from point A, B, and now we have finished traveling from point B to point C. The next line segment is going from 0 degrees all the way up to 100 degrees from point C to point D on the graph. Because we are changing temperature, it's an MC delta T problem. When I MC delta T, M stands for mass in grams. Remember that we were given moles, but we easily converted 1 mole of water to be 18 grams of water. 18, the m for the mass, times the specific heat for liquid water, grab that from that first bullet of information, 4.18, or if I include that third decimal, 4.184 joules per gram degree Celsius. Moving from point C to point D takes me from 0 to 100 degrees. That is a change of 100 degrees Celsius. Hit with me on your calculator. 18 times 4.184 times 100 equal, your screen should read as mine does, 7,531.2 joules of heat. Line segment CD is an MC delta T where we have a slope of the line representing a change in temperature. We examine the next line segment. From point D to point E, it's a flat line representing a phase change. We called that the heat of vaporization. When liquid water turns to steam, that is a phase change known as vaporization. It is a constant we're working towards remembering as 40.7 kilojoules for every 1 mole of water. And since our story problem gave us 1 mole of water, line segment DE can be easily calculated. Write down this part on your paper. Line segment DE will be equal to 1 mole of water times 40.7 kJs set over 1 mole. And very easily we can calculate 40.7 kJs of heat will move us from point D to point E on our graph. One more line segment to look at, from point E to point F. We're warming up the steam. Steam at letter E is at 100 degrees. The steam at letter F is at 125 degrees. There is a temperature change. That's our clue to remember. It's simply an MC delta T. We use the mass in grams for 1 mole of water. 1 mole of water is 18 grams. Notice the specific heat. Make sure you're grabbing the specific heat of steam provided in that first bullet of information we read through earlier, 1.84 joules per gram Kelvin, or joules per gram degree Celsius, 2 units that we are easily interchangeable. How much does the temperature change by from point E to point F? To move from 100 to 125, that represents a delta T of 25 degrees Celsius. Hit with me the mass of 18 grams times the specific heat constant for steam, 1.84, times the delta T of 25. And your screen should say, as mine does, 828 joules of heat, an endothermic positive value. We have solved 5 different line segments. The next thing we'll need to do is to sum to get the total value. However, be careful. Notice that line segment AB gave us a value of 940.5 joules. Line segment BC ended with 6.01 kilojoules. Line segment CD, we ended with joules. DE was in a kilojoule, EF joule. Before we add together, we must convert to have like units. We have to add all the same units. I took my line segments that had relatively larger numbers and divided by 1,000. Line segment AB expressed as a kJ. Slide your decimal 3 spots, 0.9405 kilojoules. I did the same for line segment CD. Slide your decimal 3 spots by dividing by 1,000, easily converting your joule to a kilojoule. Write this down as well for line segment EF. Divide by 1,000 to express that answer as 0.828 kilojoules. When we sum all 5 line segment AB expressed in a kJ, 0.9405. On your calculator, hit 0.9405. Add to that 6.01 plus 7.5312 plus 40.7 plus 0.828 equal. The positive endothermic value of 56 kilojoules of heat energy. That took us from point A at negative 25 all the way to point F, positive 125 degrees. We have calculated how much energy we needed to input into a system to move 1 mole of water as a solid ice at negative 25 all the way up to gaseous steam at 125 degrees Celsius. These problems are not hard. Take them one line segment at a time and then make sure you add like units at the end. Very easy to do. Turn your page 10. We'll try one more together in our note pack before you begin your assignment. Let's read together sample problem number 2. What is the enthalpy change? That means we're solving for delta H. Heat. How much heat? What is the enthalpy change during the process in which 100 grams of water at 50 degrees Celsius is cooled to solid ice at negative 30 degrees Celsius? We need to begin by creating the graph so that we can determine how many line segments we are solving for. Showing a graph is mandatory for these problems even on test day. I need to know, you know, how many line segments there are and what's occurring during each one of those line segments. What are the interesting points we need to graph? Start by drawing an XY axis. Temperature is on the x-axis, and heat content is on the, temperature's on the y, heat content in kilojoules will be on the x. We know we have a starting temperature at 50 degrees. Place 50 degrees up high on your y-axis. The ending temperature is negative 30 degrees. Place that down low. And what other temperature must we account for between positive 50 and negative 30? Well, that's 0 degrees, where we know water will change phase from a liquid to a solid ice. So the 3 important temperatures we need to account for are 50, our starting point, 0, our phase change, and negative 30, the final temperature. Place a dot, label it point A at your 50-degree mark. This will represent the beginning point of our 100 grams of water. The first line segment will be drawn down to 0 degrees. So draw a line from A to B. Then we know it flatlines. The slope goes flat. There is absolutely no temperature change during a phase change. All of the energy is being used to change phase. Line segment BC is flatlined. This is where liquid water solidifies. Label that delta H of fusion, DH of fusion. At point B, it's all liquid, but by point C, it's now solid ice at 0 degrees. Once the ice is formed, we take away even more heat energy and cool the ice from 0 to negative 30 degrees. How many line segments do you see we'll need to solve for? The previous problem had 5. This one I can count 3. Line segment AB, we're cooling water, MC delta T problem. Line segment BC, a phase change, that's a delta H of fusion problem. And line segment CD, an MC delta T problem where we're cooling ice. We'll have 3 line segments to solve for, one at a time. Let's go to work solving for the 3 line segments. Here's line segment 1. Write this down. Line segment AB is an MC delta T problem for liquid water. I'm stressing liquid so that we're carefully matching the specific heat constant for the liquid form of water. Problem gave us 100 grams of water. 100 grams represents the M in the MC delta T. 4.184 joules per gram degrees Celsius is the specific heat constant for liquid water. And starting at 50 and cooling down to 0 represents a negative 50 degree change. Think of that as T2 minus T1. You can also notice the slope representing heat being released. We have to be darn sure we're representing exothermic values. If heat is being lost by the system with this negative downward slope of a graph, every joule we calculate will be negative exothermic. And the negative 50, make sure that you take care of that. 100 times 4.184 times negative 50 equals, what's your calculator say? It says negative 20,920, representing joules. The joules is coming from our specific heat value, joules per gram Celsius. If grams cancels and Celsius cancels, we're left with the unit joules. But I know when we add them together, we're going to convert to kJ, so I'll just do that right now. My 20,920 joules divide by 1,000. I'm going to put my answer down as negative 20.92 kJs of heat. That's the amount of heat being lost by the system to move us from point A to point B. Now what? We have a flat line. We know that represents a phase change. Line segment BC is when liquid water turns to ice. We have to use the heat of fusion constant, 6.01 kJs per mole. That's the value at 0 degrees. Knowing that it says kilojoule per mole, we have a little mole map work to do with this problem. This problem gave us 100 grams of water. I have to convert grams to mole so that I'm matching units with the delta H. 100, right, this is what we'll write down on our paper. Line segment BC is equal to the given quantity, 100 grams of water, times the 1 mole of water set over its molar mass, 18 grams. There's my mole map work. I'm converting grams of water to moles of water. My first conversion, 1 mole of water set over 18 grams. Times my second conversion using the delta H of fusion. Notice it's negative to give me the exothermic quantity. Heat is being released as liquid turns to solid. Negative 6.01 kJs of heat for every 1 mole of water. You hit that out. 100 divide by 18 times negative 6.01, and notice this will give us a kJ directly. Negative 33.39 kilojoules of heat. We're now at point C. We have solid ice. One more line segment to calculate. We have to take that solid ice from 0 degrees all the way down to negative 30. Since we're changing temperature, we know it to be an mc delta T, where m stands for mass, c must match the specific heat of solid ice, and the change in temperature from 0 to cooling negative 30 degrees. The mass of 100 times specific heat of ice 2.09 times negative 30 equal. What does your calculator say? Mine says negative 6270 joules. I remember when I add, I'm going to put everything into a kilojoule, so I'll take care of that conversion right now. I'm going to divide by 1,000 and record your answer as negative 6.270 kJs of heat. We have our answers from line segment AB, line segment BC, and line segment CD. We simply sum the three line segments together to find the heat released. Line segment AB had a value of negative 20.92. Add that to negative 33.39. That was our value from line BC. Yeah. And the last line, negative 6.27 kJs of heat. Sum the three line segments, and we get an exothermic value of negative 60.58 kilojoules, kJs of heat. To bring us from point A at 50 degrees all the way to the bottom point at negative 30 degrees, we lost a total of 60.58 kJs of heat. This is where we'll end the video lesson from the note pack. Here is your next task. I'd like you to take out your practice test A. You've been working on that all week. You've had a chance to correct practice number 1, or objective number 1 from practice A. That was on a video lesson in a link in our Moodle. Objective 2, drawing enthalpy diagrams, and objective 3, some stoichiometry. Those you had a chance to correct using the hard copy solution station in the Moodle. That's a link. And now I'm assigning objective 4 from practice test A. Practice test A, objective 4, is available in a video lesson. If you'd like more guided practice with objective 4, find the video lessons and follow along with me. If you'd like to try these by yourself and then check your answer, what a great idea. Those who practice first and then check will succeed on their test. Those who simply copy probably won't. The assignment then for Monday. Practice test A will be checked. Objective 1 through 4 need to be 100% complete and correct. Use your resources to make sure that happens. This ends the lesson.